40 people here. So it's pretty amazing to see the growth in the meetups. All right. So real quick, about 5 years ago, I did a startup called Krugel, which was an open source search engine. The first step in that was to do a large-scale web crawl of about 100 million pages. And that was my introduction to Nudge and Hadoop and Lucene and Solr and a bunch of other technologies like that. So about a year ago, based on that experience, I started an open source project called Bixo, which is a web mining toolkit built on top of Hadoop and cascading. And as part of that, we use Tika, which is an open source package for content extraction, and we've been generating a lot of patches for that. And then I started a company called Bixo Labs, where we do web mining in Amazon's EC2. So I'm going to try 10 minutes, I'm going to talk about these things. There's three things. There's the public Terabyte Dataset project, which is a project I've been doing in collaboration with a couple other companies to generate a large public set of web crawl data that can be used in EC2 for data analysis and testing of algorithms. Part of that, we're using Amazon's Elastic MapReduce. I'm going to talk a little bit about where that makes sense to use. And then finally, yeah, really embarrassing mistakes. I think, everybody likes to talk about that really complex problem they solved where it was like really tricky code and it was a bug in somebody else's code, like in the core of Hadoop. And that's usually not where the bugs are. The bugs are usually really stupid bugs in your own stuff. And so as I was doing this project, this public Terabyte Dataset project, I kept a list. And I've got like the highlights or lowlights from that I'm going to talk about. So as I said, it's a large crawl of top US domains, 1.7 million from Alexa and Quantcast. Sponsored by Concurrent, they make cascading and us. And the goal is basically to have a free, easy-to-use public data set in Amazon. So when you want to use algorithms against that, or you want to try out, machine learning algorithms, you can. It's really easy to do it. Amazon is happy to help out with that because it's like honey to lure you into running stuff in EC2. For us, the big thing was it was kind of pushing the envelope on Bixo. Bixo as a web mining toolkit was great for like maybe 1 million pages, but when you have to scale to 100 million pages or 1 billion pages, it's a different kind of problem. So yes, it took longer than expected. I think Jimmy Liu at CMU said that the web is an endless series of edge cases, and that's really true. So every time you think you've solved a problem, there's a new problem. And there's a link that you can't see down here because Windows fonts are different than Mac fonts, which is actually on the Bixo Lab website, where if you have any questions or input on that project, you can go there and leave me something. There's a whole bunch of should have done this on the Mac. There's a whole bunch of different technologies we use. There's 3 that I'm going to talk about in particular. One is Elastic MapReduce. Another is SimpleDB. And the third one is Abro, which is a new serialization format that we use. So jumping to a practical example. The Tika project has character set detection in it. Often you can't trust what the web server returns to you about the character set, and so you wind up doing statistical analysis of the bytes in the response. And everybody kind of knows that its character set detection support isn't great. Actually, it's really lame, and the question is, can you quantify how lame it is by processing this data set? And so the approach we took is it's simple code that pulls in these Abro files which contain the content that we crawled. You look inside there for HTML pages that have a meta tag that specifies the character set, and you assume that's right. Sometimes it's not, but in general it's right. And then you do the comparison, and you generate a report, and you make it look good in Excel. I'm not expecting you to be able to understand this code. In fact, you probably can't even read this code, but the reason this is up here is it shows you this is the workflow for that processing done using cascading. And so this is pretty much all of it. I mean, there's a couple of functions that aren't in here, which is like, okay, which HTML files do we want to get? And we got to call Tika to actually have it try and guess the character set. But most of the workflow is specified in these lines here. So it's an example of how straightforward it is. And here's the results. And they're interesting results. I've got a number of pages for a slice of the data that I ran through this along the bottom on a log scale to spread it out. And I've got the percentage of time that Tika actually was correct, where correct means it was the same as the HTML tags. And what you'd like is for pages that you care about, character sets that are common, which are the ones going to be out over here, you want them to be really high. And as you can see, that's not the case. The ones in red here, like UTF-8 and 8859-1, really common ones, are down here at very low percentages. So because we have this data, now we can do things like, okay, let's try and tweak the algorithm, rerun it through, and see if we got better or worse, or let's use a different open source character set detector package. So this gives you an example of the power of having a publicly available and easy to process data set, because then you can run these kinds of analysis on it. So I mentioned, I talked about Avro. Originally, we were going to use this output format called WARC, which is Web Archives. It's something that Heritrix uses. And then, thankfully, Tom White, who's somewhere here, pointed out that WARC is going to be really hard to split. And the key thing here is, everybody talks about, is your input format splittable generally in the context of compression? Like, which compression algorithm should you choose? And the answer is LZO if you can, because it's splittable. But that also probably applies even to other stuff. I mean, if it's anything besides simple text, one line per record, you have to worry about, can you split it? And Avro is designed to be splittable, which is the key. It's also cross-language, so that you're not restricting people who want to work with these files to just doing Java or maybe C code. The other thing then is we're using Elastic MapReduce. How many people here have actually used Elastic MapReduce? Show of hands, anybody? Has anybody run big jobs in Elastic MapReduce? So a handful, okay. So the concept behind Elastic MapReduce is, leave the Hadoop to us. Like Amazon's got this service where you say, here's my job jar, I uploaded to S3, here's my data files, go and run it with 10 servers. And it takes care of, setting up your cluster of servers, configuring Hadoop, and running the job. Which makes it inherently sort of a transient on-demand thing, which means it's really good for bursty jobs. Where you're not continuously processing data, you get a chunk of data, you process it, and then you look at the results. And that's exactly what web mining or this web crawl, like what we're doing, is like. It's a very bursty thing. And the other key is it's fairly inexpensive. You pay a little bit extra than if you're using EC2, but nobody else has probably ever done this, where you've launched an EC2 job and then you leave for the day and you come back the next morning, and 15 minutes into the job it died, and your cluster was sitting there the whole night doing nothing, or you left on vacation and you came back and you realized you forgot to terminate the cluster that you'd been running before you left. So those are all examples where suddenly the cost compared to that extra 2 cents per hour per server that you paid for using Elastic MapReduce doesn't matter so much. The other issue is just in general, I mean, our friends at Yahoo here can say, yes, Garçon, I'd like a 100-server cluster, please. I don't have the money or the ops foo or time to do that, but with both Elastic MapReduce and EC2, I can do that. I can act like a big player.
I have a quick question. What about the cost of uploading the data? Is that something that you
So the question is the cost of uploading the data. It depends on how much data you're uploading. Like for us, the good thing about web crawling is typically the upload data is pretty small. It's a list of URLs, and we're storing it in S3. We're not actually downloading it, to our own systems in the end. So that wasn't significant. Depending on what you're doing, it could be a problem. So effectively using MapReduce. Just a couple things that we learned. One is there's the thing called the 10-second failure. So in Elastic MapReduce, right, you push your job up there, you give it the parameters, you say run, and you have a typo in one of your parameters. And so your job fails after 10 seconds, but you pay for the whole hour. Right? Your job ran, you paid for the whole hour. And even if it's not a lot of money, it's like the principle of the matter. It's like having a timeshare that you never visit. It just eats at you. So there's a way using the Ruby command line client where you can say alive, and then you're kind of running like an EC2 mode. You got your cluster up, you can submit jobs, and they run. And when you've got everything nailed and you've got all the right command lines carefully copied into your notebook, then you can run it like it was intended to be run. The terabyte log file. So at the end of your job, your cluster goes away. So one of the things that Elastic MapReduce does, which is really nice, is it copies all your log files for you up to S3 so you can look at them afterwards. Which is great, except if your log file is like a terabyte. If you accidentally have way too much logging going on, then two things happen. One is it takes forever for the log file to get copied up. And so you think, oh, maybe my job didn't do anything because there's no log files there. And 15 minutes later it shows up. And the second thing is then once it's up there, there's nothing you can do with it. You're not going to download a terabyte file to your desktop machine and try and grep it. And then there's a third thing. The concept behind Elastic MapReduce is leave the Hadoop configuration to us, which is great because Hadoop configuration is a pain in the butt. However, anytime you get beyond typically fairly small jobs or pretty small clusters, where cluster size might be like anything bigger than 5 machines, you start having to worry about cluster tuning where they just, for whatever reason, can't get it right. And so, for example, if you're running with 50 servers, you need to increase the number of name node threads, otherwise you get errors. So this is where this new support they have that's called Bootscript Actions is nice, because you can do that extra configuration that you need once the size of your clusters or the types of your jobs go beyond what they can handle by default. So then I said I was going to talk about SimpleDB. So why SimpleDB? The key thing here is you need to maintain the state of the crawl. You need for every URL, okay, have I visited it? When was the last time I tried to visit it? What happened when I tried to visit it? Maybe you've got to checksum on the contents for deduping. And that's a lot of data. So where do you keep that persistent state? Because I want to run my cluster and then take it down. I want to do that bursty thing, but I know I've got some data that I've got to keep around. So the first thing, of course, is the SQL solution. Except, so 2 levels deep into the crawl, I've already got 100 million URLs. And 100 million URLs is not going to work well with a typical MySQL database. Too expensive for HBase. So I looked into setting up an HBase cluster. I think I would need about 3 medium-sized instances. Running that for 3 weeks was about, 24/7 would cost me like $250. And I'm trying, this is like, how do you do it on a low budget? $250 was more money than I wanted to spend, but really, the real problem was I didn't have the energy to set up and manage that HBase cluster, because it's non-trivial. And there's so many other things going on. I was like, I don't want to deal with that. And so, to all the HBase developers and fans out there, it's not you, it's me. I'm the problem here. So then there was the third option, right? You could just save the state in a sequence file. You could copy it up to S3 at the end of each job, and beginning of each new job, you copy it down. So this probably hasn't happened to anybody out there, but for me, a couple times, you're reading through somebody else's code, and you look at it and you say, WTF, like who thought this was a good idea? And that happened the first time I was looking at the Nutch code. So I'm reading through the code. Nutch maintains its crawl state in a sequence file, and I'm reading through the code that merges the old sequence file with the new sequence file. And I'm like, Doug Cutting, he's a good programmer. Maybe he just had a bad day here, because this is stinky. And I left it. So, fast forward, that was 5 years ago. Fast forward to about 2 months ago. I'm busy debugging my code that merges 2 sequence files together that have the crawl state. And it's got a bunch of bugs. And I have this flashback, and I realize that I am recreating exactly the same code that Nutch had, except not doing it as well. And that was the code screaming at me to stop. Like this is a bad idea. So, and the other problem is the crawl database very quickly grows. I mean, forget the time spent in merging the 2 together. If you're constantly loading it back to S3 and pulling it back down, that becomes a bigger and bigger percentage of your total time. So then I said, Amazon's got this key store database there called SimpleDB. Let's just use that. So fundamentals really quick. I mean, it is a key value store. It's got some interesting extra support, like you can actually query it. You can do things like say, only update this record if this field, or what they call attributes, has this value. You can do some interesting things like that. It's got some interesting limitations, like the maximum length of a value is 1,024 characters. Everything's a string. Many of the same things that the previous talk was mentioning in the context of like HBase. One nice thing, though, is you only pay for usage, not storage. So I've got a database with 100 million URLs in there. And it's there right now, and I'm not paying anything for it. Because you don't pay for storage, you pay for usage. So I really like that part of it. Now, a key thing is, it's using HTTP for requests. So compared to like disk.io or most of the I/O you normally know about, it's got these high latency and low throughput issues. And also, higher error rates. And it's a shared resource. So that means if you're using it and somebody else is using it and it's got too much load, you start getting these, come back later, I'm busy, all full responses that you have to be able to handle. So, the first version I did said, okay, I've got a mapper, I've got one of these tables, what they call domains, let's make requests to it. Performance sucked. Then I said, well, they have batch support, so I can put 25 records at a time, so I get 25x speed improvement, and it was still really bad. So then I did a sharding thing where, and a lot of people do this, where you basically take your, record has a key, has the item key, and you generate a good hash for that. You partition the hash to as many buckets as you want, and each item then goes into a different bucket. And so I've got like 40 or 50 buckets that I'm using currently for this URL database. And that gets you pretty good performance. The step beyond this is, okay, so now you run multiple threads whenever you're doing requests. You do batch requests, and you fire up a whole bunch of threads. It's all this async sort of I/O stuff, threaded I/O stuff. And then the last thing is, this is for one mapper. So when you have lots of mappers, it starts looking like this. And now we're talking about some serious network traffic. In fact, I'm sure when I had 40 machines running, the ops team in the SimpleDB group at Amazon were like, who is this guy, and why is he hurting us? Because I pretty much was taking down their network. So that is the way that you can get reasonable performance out of the system. Now, one of the reasons I bring this up, I'll talk about it a little bit later, but you're seeing more and more of these kind of shared resources that you're working with, which have these kind of high latency, low throughput issues that often you talk to through the HTTP. And so these same approaches are common solutions to the problems. All right, now we get to the embarrassing mistakes. So this is all pretty much from 1 week. It was a bad week. My jobs, I had this fetch, parse, whatever job, standard web call stuff, and it was running really slow. So the first thing I did is you start at the bottom of the stack and move your way up. I blamed Amazon. I said, maybe Elastic MapReduce servers, they get the dregs from the EC2 pool. It's like all the machines are about to retire. Those are the ones that they give to the Elastic MapReduce team. That wasn't the case. Then, I could blame Hadoop. I mean, it is an older version. Maybe, they've done a lot of improvements with the shuffle sort phase, whatever. No. I'm using cascading. I have found a couple bugs in the past. I'm like, and I looked at it. I looked at what cascading was doing, and I'm seeing all these temp files getting written out. And I was like, the workflow planner has a bug. And then I looked at it and I'm like, no, it's doing exactly what it needs to do. So Todd Lipkin wrote a blog post called, I think he called it like simple profiling. I call it prehistoric caveman profiling, which is, you get onto the slave, you SSH onto the slave, and then you do a couple kill minus quits on your Java process that's actually doing the work, and you see where you're spending the time. And where I was spending the time wound up, the bugs weren't code bugs, they were configuration bugs. And I think this is true for a lot of people running jobs in Hadoop. There are so many different dials and levers and switches, both at the Hadoop level, the Linux boxes, your middleware stack that you're using, whatever you're using in your code, that it's easy to get it wrong. When you get it wrong, it can have serious impacts on your performance. So the real problems. The first real problem was configuration of my code. Vixo can run in two modes. One is, I'm going to get everything that you tell me to get. And there's another mode which says, hey, if I'm trying to get pages from this server and the server's still busy from my last fetch request, skip them. And I had forgotten to switch that setting to the skip mode, to the efficient mode. And now the lessons learned here is, for a lot of big data processing, if you can trim the long tail, you're going to get huge performance wins. If you look at your jobs, often you'll see like, okay, I've got 10 reducers running, and 9 of them are done, and there's one that's slowly crawling across the finish line. And if you can figure out how to make your workflow such that you can trim that and reprocess the data later, you're going to get a big speed win. Second issue, Tika also has, in addition to character set detection, has language detection. And it was on by default. And the language detection was actually taking 90% of the time during parsing, because it was generating painfully all these n-grams for every single character in every document, and building sets and comparing them to profile models. And I didn't need the language data. So that was a huge win, just changing that one setting. The third one, so we're doing a whitelist crawl. We have 1.7 million domains that we're fetching from. We need to distribute that to all of the machines. So we use the handy, convenient distributed cache functionality in Hadoop. The problem is we were distributing it as raw data that we had to process. And this processing was happening at the map phase, and we had 688 map tasks set up just because of the nature of the data we were processing. So every time a new map task started running, it would get this list of files, it would parse it, and it would generate a hash set. Okay, that was really dumb. For a couple reasons. One is, if we just turned on JVM reuse, suddenly that didn't happen anymore because it was going into a static. Another lesson, though, is don't do that. Don't do lots of cache, pre-process it. And the third thing is, if you really do need to worry about that, then do it in your reducer where you have more control over how many reducers run. And the last thing was we were generating terabytes of log files. So we were generating log files versus results. We're spending a lot of time logging. So summary. The public terabyte dataset is getting there. So we've actually released some samples of it. There's a blog post about it. There's a link coming up on the next slide. It would be great to get input on it. Primarily, the Avro format that we're using is the data there that, if you're going to use this, you would find interesting and useful. And it's going to be free, and it is pretty easy to use in EC2. I talked about where Elastic MapReduce works well, and the fact that, finally, many bugs that you run into are actually configuration problems, not real coding bugs. So there's the blog post about the sample data. So I had another talk that I was thinking of giving, which was doing machine learning in EC2. We have this service where we classify links as spammy or not. So we actually get the link and we do data mining. We follow the link, we get the content. It's an alternative approach to classifying spam. If I'd known that the first talk was going to be about spam, I would have done this talk about spam because it would have had a nice theme going. If that would be interesting to people, I can spend the time to turn it into a real talk. So if you go to that link, let me know, and if enough people say yes, then I'll spend the time to turn it into a real presentation. Because it's kind of interesting. It's like Mahout and doing this thing called semi-supervised machine learning, because it's a common case with web-scale data. You have a small set of labeled data, and you got a lot of unlabeled data. And this kind of what they call PU learning, semi-supervised learning, lets you leverage the unlabeled data. And I think it might be applicable to other types of problems like that. So if that's interesting, go to that link and let me know why or what specifically is interesting about that. And then that way, when I do the presentation, I can let you know about it. All right. Yes. Any questions?
So how exactly did your poor man's profiler, kill minus quit, how did that work?
Well, every time you do it, it dumps output to the standard out log. And then you just look at the standard out log, and you'll see a list of all the threads that were running. And if you do it like 5 or 6 times, you'll see, well, every time all these threads are blocked except this one thread is running and it's doing X. And okay, why is it doing X?
So you were looking at the stack traces?
Yes, basically looking at stack traces of thread dumps.
And can you put the previous slide on so I could take it?
Oh, sorry.
Did you think of using GTM instead of SimpleDB?
No. No, I was kind of in the mode where...
Well, there's the SimpleDB wrapper for it.
Right, so I used some wrapper code for it. The issue is when you get to real scale like this, you have to carefully manage your thread connection pool, essentially. And so that's why I wound up going with the lowest level sort of library that I could find that would let me talk to SimpleDB and then modifying it to do what I needed it to do. So ultimately, we wound up writing a cascading tap. So we're using cascading for all the workflows. So we wrote a tap that lets you use SimpleDB for input and output. And we did the same thing for Avro. I should have mentioned that. I'm like, oh god, we gotta somehow create a bridge between cascading and Avro. But in the classic just-in-time open source development model, like the week before, some code was submitted to the Avro project that gave us the support we needed. So thanks to Doug and Scott for doing that. And in a couple days, we had a working connector. Anything else? Oh, all right. Thank you very much.
We promised you a raffle, so here goes. And
did everybody get a chance to put one in? 1 and 2?
So
You have 30 seconds.
we got, yeah. If you want to join the raffle, you have a last chance.
Just take one.
And I remind you that you have